Hey everyone, today I want to talk about a binomial distribution. So I have an example of a question up here. It says a certain insecticide kills 70% of all insects in laboratory experiments. A sample of 11 insects is exposed to the insecticide, and in that experiment they want to know what the probability that exactly 2 insects will die. Now, this is kind of the premise for a binomial distribution. I'm going to take that information up here and just kind of simplify it. We're looking at 11 insects. Each insect is basically a member of this sample. It's an individual event. 70% of insects will die, and they want to know the probability that exactly 2. The reason that this becomes part of a binomial distribution is because you either die or you live. This is the example of something that is binomial. The reason that we say it's binomial is because it has 2 options, right? There's 2 things that can happen. You die or live. You flip a coin, you get a heads or tails. You play a game, you win or lose. As soon as you add in a third option, like you could win, lose, or tie, as is the case in some sports, then it's no longer a binomial distribution. So if you're looking at something where there's only 2 options, yes or no, black or white, win or lose, on or off, those are binomial by nature. So this becomes kind of a simpler problem as far as a binomial distribution, because we're looking for the probability that exactly 2 things happen. Now, I'm going to show you the math behind this and then show you how it becomes more complicated when I ask the question, what's the probability in a case like what's the probability that 2 or more die, or probably 2 or less, or in some cases I just say less than 2. Those all become not horribly difficult problems because of the ability to use technology, but if you were to look at the process for solving it, it becomes tedious and long. So I'm going to show what's happening. I'm not going to do those whole things or that entire thing by hand, but one of the things that I'm going to start with this same question is, what if we had the same idea, but I wanted to know what's the probability that all the insects die, right? Most people would remember that since each of these things is an independent event, the probability that 11 die, right, or the probability that x is equal to 11 would really be just taking the individual probability that an insects die and multiplying it. Here would be the probability that 2 of them. Here would be the probability that 3 of them. And I'm going to do this until I have 11. So this would be 1, 2, 3, all the way till 11 insects die, right? Simply 0.70 to the 11th power. That's the probability that all 11 insects die. And as an example, pull up a calculator here because I can't do any of this stuff in my head. Here is 0.70. Let's see if I can, in this calculator, go ahead and do 0.70, and I'm going to raise that to the 11th power. And so I have a 1.9% chance that this is going to happen, moving the decimal place over. Right? So a 1.9% chance that all 11 insects die. If I wanted to do this for exactly 2 insects dying, the problem is that if you were to think about kind of the tree diagram for doing this, I would say, well, here's the probability that an insect lives and dies, right? I could have then the second insect live or die. I could then go on to the third insect, live or die. And you would notice that I would have to do this for 1, 2, 3, all the way down to 11 insects. And the problem would be each one of these branches is a different probability. So we talked about that in the previous chapter in using a combination of events. So I am basically going to say I want to take 11 insects and I want to choose combinations taken 2 at a time. How many different combinations could I come up with of 11 insects where they would die 2 at a time? Now, if you recall from when we were doing that in the last chapter, the formula for that, I'll rewrite it here, comes in kind of the format NCK, where I am going to take n factorial divided by n minus k factorial k factorial, right? In this case, I have 11 factorial divided by 11 minus 2, which is 9 factorial, and then 2 factorial. So I am going to take a moment and figure out what that is using my calculator again. Let's see if this one has factorials in it. I'm not really sure that it does. Sure enough, here we go. 11 factorial, all right, divided by, and I'm going to put in parentheses, 9 factorial times 2 factorial, close the parentheses, and hit equal. So I have 55 different ways. That's how many combinations of ways that 2 insects could die. All right. The problem is we don't stop there and say, like, I didn't ask how many different ways. I asked what's the probability that at exactly 2 insects would die. So when you're working with the probability that 2 insects would die, and I'm going to write the formula first of all. Let's put this in a different color here so that it stands out. The probability formula for a binomial distribution really says this. If you are going to have the probability that the number of insects die is equal to 2, right? Capital X is equal to small x. I am going to take this, what I've already done up here, NCK. I'm going to take that NCK, or that idea, and I'm going to kind of rewrite it as NC, and then I'm going to have, I'm going to use this lowercase x. That's the number I'm looking for. Like, how many different ways can lowercase x happen? How many different ways can 2 insects die? I am going to multiply that times the probability that an insect dies raised to the x power, right? So far I'm saying 11C2 times the probability. If you remember, that was 0.70 raised to the second power, right? Basically, if you're following along here on the first part of this formula, I have said there are 55 ways that an insect can die, or 2 insects could die, and the probability of 2 insects dying is 0.70 to the second power. And let me quickly put that up here. 0.70 to the second power is 49%, right? But I also have to include all of the insects that didn't die. Like, what's then the probability of that? So the rest of this formula, 1 minus p to the n minus x power. So what is that saying? 1 minus p is basically saying that if there's a 70% chance that an insect dies, there is going to be a 30% chance that an insect lives. Also, what is this n minus x saying? Well, this is saying in this case that there were 11 insects total, right? You were looking for 2 being dead. That means if 2 die, 9 are going to live. So over here I've got 0.30 raised to the 9th power. So the probability of that happening, I have as 0.000019683, and I'm just gonna cut it off right there. I don't know if that's rounded or not, but Here then is the final for a binomial distribution, to figure out how many ways could an insect die. And look at what we have here. How many different combinations are there for 2 insects to die? 55. What's the probability that 2 insects die? 0.49. And what's the probability that the other 9 insects live? 0.000, all that stuff. So let's throw those together. This times 55 times 0.49 says that the probability that exactly 2 insects die is going to be 0.0005, or there is a 0.05% chance that 2 insects die in this problem. All right, so I've thrown in this answer of 0.0005. Notice that it was asking for it as a decimal. That, again, is the same as 0.05%. All right, so be careful with that. If you're writing it as a percent, it's 0.05%. If you're writing it as a decimal, in this case, 0.0005. These two things are synonymous. So that's kind of the breakdown of this entire thing. All right, let's take a look at some of these other problems that I had written over here, because this is where you're going to want a binomial distribution calculator, as if you didn't want one already for that. What if I wanted to find the probability that 2 or more die, right? Notice the or statement in there. Now I'm finding the probability that exactly 2, or plus the probability that x equals 3, plus the probability that x equals 4, plus the probability that x equals 5. And you can see how this is going to go all the way on until the probability that x equals 11, right? That's going to be a pain. Let me show you without actually crunching the numbers. I would have to say, all right, probability that x equals 2. Well, there's 11 things. I'm taking 2 of them at a time. I want the probability that one of them lives, or 2 of them live, 2 of them die, times the probability that 9 of them live. Plus, well, now I have to do the 3. So over here, I've got 11 combinations taken 3 at a time, times the probability that 3 of them die, times the probability that 8 of them live. Do you see how these numbers are counting down, or they're changing? If I want 4, I have to add 11 insects, 4 of them die. The probability that 4 die times the probability that 7 live, right? This keeps on going until I get the probability, or I did 11 insects taken 11 at a time, times the probability that all 11 die, times the probability that none of them live, right? So as you're going through this, that's a lot of addition and subtraction to keep track of. So let me show you, first of all, how you could do this within Google Sheets, right? So Google Sheets has a binomial distribution built in. So here is binomial distribution, right? When you are doing this, it does them exactly, which makes it a little bit trickier, but you could simplify this a little bit. It does it exactly because I'm going to say there's 11 insects. That's the number of successes. The number of successes, let's go start with 2. 2 insects are supposed to die. There's 11 insects. That's my number of trials. The probability that an insect dies was 0.70. And this idea of cumulative. When you say true or false to this question, what you're really saying is, do you want me to add up all of the probabilities up until that? So if I said true, that would actually be taking the probability that x equals 1, and the probability that x equals 2, and I believe even the probability that x equals 0. And it's adding those together. 0 plus 1 plus 2, that's cumulative. The probability that none die, 1 die, or 2 die. right? So when you say true, you're really answering the question that I asked before, like, what's the probability that 2 or less? Okay, so it gets tricky with that because some people will struggle thinking through the parentheses on this. So if I just want the probability that exactly 2 die, I could do equals binomial distribution, and I want to say 2 out of 11 die, a 0.7% chance that they die, or a 70% chance that they die, and false. Notice this matches the number we had gotten before. So one option for doing this, that some people like, but I think it does get a little bit tedious, is they could do this for 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If you needed to know the probability that 2 or more died, you could do binomial distribution. Now let's do that 3 out of 11 die. Same things. I don't want it. I want false, etc. Kind of going through that. Okay. I don't necessarily like doing that. If you wanted to make it a little bit easier, you could possibly put together a list of numbers and say like, oh, here's all the different ways to do this. It does get a little bit tedious when you're doing that. So instead of doing the binomial distribution that way, what I would recommend is using a binomial distribution calculator. So in Google, I have Googled a binomial probability calculator. StatTrek is the one that I recommend. I really like it because it gives all of the options. What you have to do is interpret. So in this case, we are saying the probability of success on a single trial, 70% of the insects die. There's 11 insects, and I'm looking for 2. 2 is the key number there. Notice that's all I have to tell it. When I calculate it, I get all of these answers that are down here that says, here's the probability that exactly 2 die. Here's the probability that less than 2. Here's the probability that less than or equal to 2, greater than 2, greater than or equal to 2. So make sure you understand what your probability was, what that 2 represents, and then figuring these out is just exactly, less than or equal to, greater than or equal to, and you have the statistics there. So we could do that with a couple ways in Google Sheets, but for the sake of simplicity, I recommend getting comfortable with a binomial distribution calculator. So let's take a look at a couple problems here quick. First of all, researcher wishes to conduct a study of the color preferences of new car buyers. 50% prefer red. 20 are selected randomly. What is the probability that exactly 15 buyers prefer red? Well, the probability that someone prefers red is 50%. There's 20 trials, and I want 15 buyers. I'll calculate that. Because I'm looking for exactly, I'm looking at this line here, where I'm finding that 0.0147, or really 1.49 or 48% prefer red. Let's do another one. Same question. 50%. Let's do a different one that doesn't have 50%. Let's go back to the beginning of this. Here, assume the random variable x, so it could be anything. That's going to say that I want to know what's the probability that exactly 11 things happen out of 18 total things with a probability of 80%. Putting that in, 80% chance of success, 18 trials, 11 successes, and I want exact. The nice thing when they write it this way is you can see x equals 11. Here's x equals whatever it is. There's my answer. 0.034, looks like I'm going to 0.03499. I have to round that off, so that's going to be 0.0350 if I'm doing 4 decimal places. I'm going to skip a couple of these. I want to see the word problems. These ones, pretty straightforward. They all follow the same format. Here's a word problem. Be careful about whether they want success or failure. A researcher conducts the study of the preference of new car buyers. This one has a 40% prefer green. 12 buyers, 10% prefer green, or 10 prefer green. So 40% like green, out of 12, how many like green? The reason I'm saying pay attention is sometimes they throw a curveball and they say, what's the probability that 10 would like something other than green? So that means you would turn this around and say, well, out of 12 people, 60% do not like green, and so I would use that as the kind of the, what do you want to say, the complement of that. But anyway, hopefully that will help you out kind of getting started with binomial distributions. As always, if you have any questions, don't hesitate to reach out.